So 3.1 derivatives, this is continued. And we saw how we got the way to calculate the derivative is by looking at the secant line, right? And then taking the limit of that. So which gave us the slope of the secant line. It's just, there are plenty of different notations for this, but we use one of them, x of x, f of x minus f of a over x minus a. And then when we went to find the derivative, that was the slope of the tangent line by taking the limit as x approached a. So the distance between x and a got extremely small, right? Very small. They're almost identical of the same expression. All right, so let's do, not sure if we did this exact problem, but if we did, it might still be going from your memory, but we'll do it again. F of x is equal to negative 16x squared plus 96x. What is f prime of x? Remember, the derivative is a function, right? So somebody said that earlier too. It is a function. It's just another expression, another algebraic expression to do a calculation. So f prime of x, its definition, this is exactly what you have to do on the test. So put a star on it. You got to do this format. Now you're going to see the tips and techniques later on. You can be like, do I really have to go through all this to get the answer? You will know what the answer is, but just show the steps on how to get to it the formal way. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. You need to memorize this. I'm not giving you this formula. You may have seen this before, even in college algebra. You've done this called the difference quotient. You just have not taken the limit. But all we do is evaluate x plus h into the function. So I'm going to use some brackets just to distinguish it. So negative 16 times x plus h right there gets squared plus 96 times x plus h. And that's that first part right here. Highlighter. And then minus the f of x, that's always just given to you. So just rewrite it, negative 16x squared plus 96x. It's this part. And now that's over h. So now here it's just really ugly, messy algebra. Just got to simplify some things. I think I told you last time, I usually will not give you anything higher than a second degree polynomial, because that gets really messy and ugly. So I'm just trying to illustrate, or you're trying to illustrate to me, you know the process of finding derivative by hand, manually. All right, order of operations, exponents come first, so we'll have negative 16 times x plus h all squared, x plus h times another x plus h. Don't make the mistake of just saying x squared plus h squared. That's a very common algebraic error. Most people do. That's binomial times binomial gives you a trinomial. So it's x squared plus 2xh's or hx's, however you want to put it, plus h squared. Plus the 96, I'll distribute x plus 96h. And now distribute the negative all the way across the other bracket. We'll have positive 16x squared minus 96x all over h. The part that you're subtracting off f of x right here usually always disappears. So you'll see all those factors or terms should cancel out. We got a positive 96x, negative 96x. A once I distribute this across, negative 16x squared, positive 16x squared, that'll go away, right? Let's just write that out. We got negative 16x squared minus 32xh minus 16h squared plus the 96h plus the 16x squared. H, like I said, those negative 16x squared, positive 16x squared, that disappears as well. Everything left in the numerator has a factor of h. That's what you always want to have, so that when you factor it out, it will cancel with the factor in the denominator, right? So therefore, you can now evaluate the resulting polynomial. So this is still the limit as h goes to 0. I still want to keep writing that because I didn't take the limit just yet. I'm going to factor out the h from all the remaining terms. And you get this, right? H is now disappear. Now you take the limit. When h goes to 0, your derivative is going to be equal to negative 32x minus 16 times 0 plus 96, which is just negative 32x plus 36 plus 96. That's your derivative. This will calculate the slope of the tangent line at any given x. All right, so let's kind of look at the graph of this, the original function. Now this is why calculus is important, because you can't always see a nice, pretty graph of all functions out there in the real world. But if you know the calculus behind it, you can answer all kind of questions about the properties of that function without you actually looking at it. So the graph of f of x, which was our original negative 16x squared plus 96x, is quadratic, right? Opening downward because of the negative 16, right? So a general shape of this, just like one of these projectile motion kind of graphs, right? Think about plus 0, that's your initial height. You can call that projectile motion stuff. So we got a parabola looking like this, right? Something like that. All right, so if I'm at 0 right here, f prime of 0, so f prime of x is equal to negative 32x plus 96. Put in 0 there, you get this to be 96, right? So this is a positive slope of 96 right there. Now, if I go out to 1, slope is still positive right there, right? But it's not as steep. So f prime at 0 is 96, f prime at 1, negative 32 plus 96, that is 64. When I get to 2, it's less steep, right? But it's still positive. Calculated, f prime at 2 is negative 32 times 2 plus 96 is 32. At 3, f prime at 3. Negative 32 times 3 is negative 96 plus 96 is 0. Slope of the tangent line is 0. It is flat. It's a horizontal line right there, right? And I'll go out to 4 and 5 and 6, and you can see all the slopes are changing to be steeper, but negative, right? As you progress along. This one, f prime at 4, evaluated in there, you will see this is negative 32. Mirror images, right? This would be f prime at 5 would be negative 64. And f prime at 6, that's supposed to be a tangent line. That's negative 96. So that's a visual illustration of how the slope of the tangent line in relation to the actual function. Any questions? Just riding a roller coaster, that's all it is. How are you doing? All right, derivative notation. We already saw one of them. All right, let's just say if f of x is our function, a way to show its derivative, one easy way is f prime of x. That's the most common way. And we saw its calculation, its definition to calculate it out. There's a limit as x approached a, that's one of them. As h approached 0, that's one of them. Here's another one. The limit as the change in x, delta x. Yeah, I've heard of that before. A delta triangle means change. Approaches 0 of our function x plus that change in x, so a little more than x, minus f of x, all over that change in x. Same exact thing we've done before, right? Slope is change over of y over change over x, change in x, right? Same thing. So this is a f of something, that's a y value. F of x is a y value, two different y values, whereas two x values that are very, very close to each other. So you could write it this way as well. The limit as the change in x approaches 0 of a change in y, just as this, over a change in x. Now in calculus, instead of writing triangles all the time, triangles are a pain in the butt to draw, right? You always want shortcuts. dy over dx. So delta y over delta x, that's the same thing. Just write a d instead of a triangle. Go figure. So dy over dx is one of the other very useful notations. I think I tell y'all on the first day of class maybe how Isaac Newton is known as the founder of calculus. And he wasn't the only person that did all the work. Another person that did a lot of work was Leibniz. I think his first name is Godfrey. I can't remember. Anyway, he did a lot of contributions to calculus as well. And in fact, some people will say he's actually founder of calculus. That's the notation he used and derived and used all. So dy over dx, that's called Leibniz notation. We will use that periodically. I've mostly used just the prime notation, especially if you're given nice polynomial functions, those kinds of things like that, or it's already in function notation, it's just a prime mark on it. But this now says, take the derivative of y with respect to the x. Your independent variable is x. So it could also be written as this. So take the derivative of y. Y is the function, right? Or maybe just the equation with respect to x is your independent variable. You could see it this way, df over dx. Whatever the variable is in the bottom, that is your independent variable. So just always say, I'm taking a derivative of this expression. My variable is in this expression. That's one way. If it's not specific as a function, you might have y equals blah, blah, blah. That's just the equation. We have y equals graphs that are circles. We still take derivatives of that, but it's not a function. So we'll do y prime. I've seen capital D, derivative of f of x, something like that. I've seen capital D over dx. There's all tons of different notation. You can make up something if you want, really. Yeah. Then you can become your own textbook author and start selling them, right? Become mega rich, write your own calculus book. Y'all can do that. All right, so evaluating derivatives. We did some just now, but the notations for that could be f prime evaluated at a. We just did that. That was easy. Maybe it's not a function. Maybe it's just some equation. Y prime evaluated at a. The derivative of the function with respect to x with a vertical line and saying x is equal to a. Now it just means evaluate the function at a. Or you might have just dy over dx evaluated at x equals a. So plenty of ways to do that. And I'm pretty specific. Like if I ask you to find the derivative, like I tell you, most of the time it's going to be, for me, like that. Okay, so f prime at a number, 2, 4, whatever. It's pretty straightforward. So just in case in my math lab or in the textbook, if you're reading and you see do this, you're like, what they want me to do. They say plug this into the derivative, right? Plug that into the derivative. All right, let's find the derivative of say dy over dx if y is equal to the square root of x. This is a very important one. You will probably want to memorize this derivative just so you don't have to go through all the calculations or the techniques to calculate the derivative in another format that we'll learn later. But we're going to go through the entire process just the same exact way we've done f of x minus h, f of x plus h minus f of x all over h. And it gets a little messy. So your algebra skills have to be pretty good, okay? This is the limit as h goes to 0 of f of x plus h minus f of x all over h. Which is the limit as h goes to 0. I'm putting x plus h wherever I see the x, right? So right there is now going to be x plus h. This is the square root of x plus h minus f of x, which is the square root of x, all over h. My whole point is to try to evaluate 0 in place of h, right? I can't do it. I still got h in the bottom. It will make it undefined. All right, so how about we do a little fancy algebra? Let's rationalize the numerator. There's another way. I won't show you that. It's like, where in the world are you getting that from? So this is the more logical way. multiplying the numerator by its conjugate, right? Square root of x plus h plus a square root of an x, top and bottom. All right, so the top, boil it out. The square root of x plus h times the square root of x plus h is just x plus h, right? That's the first. Outer, square root of x plus h times the square root of x, that would be positive product. Inner will be that same product, but now negative. It cancels away, right? And now we got the last. A negative square root of x times a positive square root of x is a negative x. X minus x goes away, right? Factor of h on the top cancels the factor of h on the bottom. So now we're looking at just the limit as h goes to 0 of 1 on the top, the square root of x plus h plus the square root of x on the bottom. Can we now put in h as 0? Yes. So we'll get a square root of x plus 0 plus a square root of x. How many square roots of x do you have in the bottom? 2. So 1 over 2 square root of x, you don't have to rationalize this. You're going to see a lot of this stuff. The whole point of getting to the derivative is to plug numbers into it a lot of times. So it doesn't matter if you plug it in the top or the bottom. If it's rationalized, you're still going to get the same answer. So once you get it as a nice, decent looking expression, just stop right there. Okay, so this is dy over dx, or your y prime, if you want to say that. It's 1 over 2 square roots of x. That's the derivative of the square root of x. All right, so from here, find the equation of the tangent line at x is equal to, let me put this order pair, at the order pair 4, 2. I have one point. That point's on the tangent line. That point is on the function itself, right? Because square root of 4 makes 2, right? Square root of x, that's our function. I just need my slope, right? So dy over dx, evaluated at x equals what? 4? Is 1 over 2 square root of 4. This is 1/4. That's my slope of the tangent line, right? So now to find the equation, y equals mx plus b. Y is 2 for a slope of 1/4 when x was 4. This solves for b. 1/4 of 4 is 1. Subtract it from 2 makes 1, that's b. So y is equal to 1/4 x plus 1 is the equation of the tangent line. All right, y'all can watch me do this all day long, right? Can you do it? Find g prime of t if g of t is equal to 1 over t squared. See if you could set up your definition of a derivative as limit as h goes to 0, or g of t plus h minus g of t all over h. So it's going to be a little bit messy looking algebra, but you have to figure out. We'll simplify it down to where you can get this derivative. I'll give you about 10 minutes on this, or if anybody needs to get out, take a break, feel free to do that. G prime of t should be equal to negative 2 over t cubed. If you've taken calculus, you probably got straight to it, right? But were you able to do all the algebra to get to this? Okay, let's see. So g prime of t is equal to the limit as h approaches 0 of g of t plus h minus g of t all over h. Make our substitutions. All right, so g of t is 1 over t squared, so g of t plus h is 1 over t plus h squared. Minus g of t, which is the 1 over the t squared, all over h. From here, it's just algebra cleanup. There's a couple ways to do this one if you want. If you've got one fraction divided by a fraction, that's one fraction times the reciprocal at the bottom, right? You could do that. There's only one fraction, h in the bottom, right? Or this is actually a complex fraction, which I got fractions within fractions, right? So a way to do that is I can get rid of all the fractions inside by multiplying by the LCD of all the denominators there. So I see that if I multiply everything by the LCD, which would be this factor and this factor, right? It's everything. T plus h squared and t squared. Think about this h is over 1, right? If you want to think of it that way. T plus h squared over t squared. So that you can see t plus h squares cancel there, t squares cancel there, and that's it. Now we simplify this a little bit further. So my numerator, this term just is t squared. This one is minus t plus h squared. The bottom is just ht squared, let's put it that way, ht squared and t plus h squared. My numerator, notice I could factor that if I wanted to, right? This term is perfectly squared, the minus another perfectly squared term, difference is perfect squares. So that factors is t plus h and t minus t plus h. All right, so in the numerator, we got t plus t makes 2t plus h. This we have t minus t is 0 plus h, so that's just times h. And that is exactly what we want to happen, right? All factored out so that you can cancel common factors in the top and the bottom. H's go away, does not no longer create the denominator to be 0. So when the h goes to 0, the limit is 2 times t plus 0 on the top over t squared times t plus 0 squared on the bottom. And this gives us 2t on the top and t cubed on the bottom. And I am missing something, didn't work out right. I missed something because I know my derivative was supposed to be negative 2 over t cubed. What did I do? Yes, I did probably. The h is negative up here, right? That's that right there. So at least a -1. That. And still something. I shouldn't have that t on the top. Ah, yeah, t to the 4th on the bottom, right? T squared times another t squared is t to the 4th. See how easy it is to make a careless error. Let's do this. This is t to the 4th right there. And that all simplifies to -2 on the top and t cubed on the bottom. And that is your derivative g prime of t. I can tell you most people in calculus, and even me, the error isn't with the calculus, it's with the algebra. That's the biggest problem. Okay, so I will tell you too, on my test, I'm not penalizing you heavily on the algebra stuff, penalizing more on your knowledge of, or not knowledge of the calculus. Okay, so if you can know your steps and look at, even me, I made a minor mistake in there, I would only probably take off 1 point on that, if that many, okay? But if you know somewhere in there what the actual derivative was supposed to be, like I showed you at the beginning, you knew it had to be that, and you say, I know it has to be this, it's some just error somewhere in there explaining that, and I probably won't even take anything off for it. So, okay. But the reason I know it is this without having to do all the work, there are shortcuts. I can look at most problems and just say, I can see the derivative. I know the shortcut is, okay? For this, again, this is the formal way. So in case there is a problem, you don't know how to find the derivative using a shortcut, every one of them can be done this way. It's extremely tedious, and you just got to watch out for your careless errors. All right, let's look at the graphs of derivatives. All right, let's say we have a function that looks like this. It's piecewise defined function along some interval of x. It doesn't have to be exact, but just draw as best you can, I guess. All right, so this is f of x. I say from here, draw the graph of its derivative. Okay. You will draw pretty much directly underneath it, same scaling on your x and y axis that you see. Now, if I say right here, this slope on this part of the graph is going downhill, right? I know it's negative. Let me just tell you it's -1. From here to here, now you're going back uphill, right? Slope is positive. Let me tell you it's +1. And then from here, all the way from here, all the way to this point, the slope is negative, right? And I tell you it's -1/2. Now you can actually do some calculations to figure out this, right? Changing y over changing x. You can pick 2 points on that part and do the calculation to figure out its slopes. But if I give it to you, over here, all you have to do is say, okay, from -infinity, basically, let me put an arrow on here, I guess. On there. -infinity to -2. The slope is always -1, right? It's constantly -1. So all I have to do is -1, draw a flat line, right? All the way up to -2. Now, I will put an open circle there. And we'll talk about why that's an open circle in a second. Because it goes all the way up to -2. The slope is that. Think about it too. At a point, can you have a slope? Slope is a measure between 2 points, right? So if I say at -2, x is equal to -2, do you have a slope? No. If I'm on one point, that slope is wobbling all around, right? So there's no derivative at a point either. And so this chalk point right there, open circle. And then when I get to -2 to 0, the slope is always +1, right? So the slope is always +1 right here. Again, I'm going to put an open circle on the +1, -2 that is, and at the 0, an open circle too. So my endpoints right there in these, I'm putting open circles. And then from 0 all the way to infinity, my slope is always -1/2. It's always flat. I shouldn't say flat, but it's always constantly on there. There's no bumps or humps or anything in there. It's a nice ramp, right? So 0 to infinity, slope is -1/2. So everything that I've drawn here, this is y is equal to the derivative, y prime of x. And f prime of x is not defined at x equals -2 and x is equal to 0. You see how you interpret that? Okay, so what you're plotting are really flat lines. They're constants in this for this particular one, right? So the constant slope along a linear line, right? No matter what 2 points you pick on a linear graph, the slope is always the same. So these 2 points, this point, that point, it's always going to calculate to be the same. It's different when you're looking at polynomial functions, though. slope is constantly changing. It's never the same on any 2 points. Well, it could be on 2 points, but if I have, let's look at g of x, see if I can draw this one. Now this, I can't tell you what the slope is, right? Because like I said, if I pick a point here, now I can take the slope of the tangent line at that point and tell you, but I can't take this point and this point and get you the slope of a point right here, right? My instantaneous rate of change is always different everywhere along that curve. But I do know something, that if I pick any tangent line on this side right here, notice they're all positive, right? Slope of the tangent line is positive until I get to here. Put in a different color, red. So at this peak right there, it levels off. Your slope of the tangent line is 0. When you get here, all these tangent lines is negative, right? Then we get back to this peak, or valley, I should say, right? Slope is 0. Then we repeat the process, right? Positive, 0, and then negative. All right, so at that max right here, let's just say that is -3. At this minimum value, a local minimum, that's at -1. And then this maximum, local maximum right there, that's at +1, I think that is. So if I say, draw me a picture of the derivatives graph. Same scaling along the axis. From -infinity to -3. We stay positive. Why? The slope value is positive. So our y value is positive. We're above the x-axis, positive, right? Until we get to -3, the slope is 0. Y is 0. That means we're back at the x-axis, right? So right here is 0 for y, right? 1, 2, 3. Let me just put positive like that. Negatives down here, right? Negative like that. Don't need specific numbers, but again, look at the steepness of the line, right? Slope is a positive big number, right? And it gets smaller and smaller, but still positive until you get to this 0, which is now close to 0 when you get here, but it's a very small number, positive, right? So you think about your slopes here, starting off high up here, and your y values are getting smaller and smaller and smaller until it gets to 0, right? When we're between -3 and -1, we have negative slope. So we need to go below the x-axis. So it's going to represent all this, and then coming back to 1 to get to 0. Between -1 and +1, we got positive values. So we're above the x-axis on the derivative graph. We got to come back to 1 because our slope is 0. So we're going to be looking at something like that. And then beyond 1, we're totally negative, right? All the way to infinity. So that means we're like this. That's not a 100% accurate graph, we don't know what the actual function rule is. So if we don't know the rule, we can't get this derivatives rule. But that's represents, I can go backwards and forwards too. I can look at this and say, all right, my slope of my tangent line is negative between -3 and -1. So therefore my graph has to be going downhill on the original function. And we are. So these are lots of interpretations. I really won't ask you to draw a lot of this because there can be 100,000 different graphs that can represent the same information. So slope is positive here, right? Slope of the tangent line is positive here. On its graph, it is increasing. It's going uphill. It gets a little confusing when you look at this and you say, that's not positive. This is the derivatives graph, which means it's in the positive region above the y-axis. It's positive. Okay? So now that slope is positive, meaning the graph goes uphill. We're not looking at the original function. This is g prime of x. Differentiability and continuity. Differentiability implies continuity. So for the derivative to exist, the function has to be continuous. Now, just because it's continuous doesn't mean the derivative always exists at certain points. We just saw that with those sharp points. I can go back up. The derivative did not exist at -2 and at 0 for these, right? Because that is a sharp point, sharp turnaround. But the function is continuous. So if you have a continuous function, you can calculate derivatives. All right, so if f is differentiable at a, then it is continuous at a. I'm not going to go through the entire proof. We saw what the proof of continuity was. You kind of was supposed to do it on the test a little bit, right? Show that the limit was this value and also show evaluation of the function was this value. If the two existed or equal, that meant the function was continuous. Okay, but y'all can look it up if you want, but graphically it's easy to see. If I have something like this, here's a piecewise defined functions. Many of them are not continuous, right? Such as that. So this is not continuous at a. So f of x is not differentiable at a, right? Again, think of that idea of trying to put a tangent line on this. You put a tangent line on this point or on this point that really doesn't even exist, this tangent line can wobble, right? It's nothing to be one specific tangent line, right? So this is not continuous, applies not differentiable. Differentiable implies continuous. So let's see if we can do a continuous function, but not differentiable. There we go. Right there, sharp point. So anywhere you have sharp points, you can't put a tangent line. It's the same thing. It's like that endpoint. That tangent line will just wobble around it, right? And there's one other place where F has a vertical tangent line. So if I put a vertical tangent line right there, at that point right there, what's the slope of a vertical line? It's undefined, right? So that's why it's not differentiable. Slope of the tangent line is undefined.
So when you say it's not differential, which means I have something undefined. That's what I'm saying.
You can't find its derivative. Yeah, it's not going to give you any numerical value or any function that will calculate any numerical value for you. Yeah.
So what is no one? That's for that I'm
Yeah, that's still a sharp point. So you might see like you'll see some function that looks like that. It's plus, that's still a sharp point right there, undefined. The derivative is not defined there either.